Today we're going to talk about the ideal gas law. Before we really get into the ideal gas law, let's talk about the combined gas law really quick. It's P1 V1 over T1 equals P2 V2 over T2. It's really kind of an application of the ideal gas law, but it winds up being a little simpler just because you're relating an initial condition to a final condition. So when you have the combined gas law, all of these that are labeled 1, that's your initial, and then labeled 2, that's your new condition. Okay. And then P is pressure, V is volume, T is temperature. Temperature must be in Kelvin all the time, always, whenever we're doing these calculations, because Kelvin has no negative numbers. It can't mess up the calculations. And then pressure and volume, as long as it's the same on both sides, you're good. But this combines a couple different theorems together. It combines Boyle's law, Charles' law, and Gay-Lussac's law all into one nice equation. And you can see the relationships between these properties. Pressure and volume are inversely related. I'll put that down. Pressure, volume are inversely related. That's assuming that the temperature is held constant. As you increase the pressure, the volume will decrease. Pressure and temperature are directly related, assuming the volume is held constant. And then volume and temperature are also directly related, assuming you keep the pressure constant. So make sure that you know those relationships between these different gas properties. And again, it's assuming that the third one is constant. Now the ideal gas law is PV equals nRT, and it relates pressure, volume, moles of a gas, the gas constant, and the temperature in Kelvin. So this is the equation that includes moles, so if it's asking for moles, make sure you're using this one. Couple things here. So I recommend every time you put pressure into ATM, volume should always be in liters. N is, of course, moles. T has to be in Kelvin, and R is your gas constant. Your gas constant is 0.0821. But this value only works if you have it in ATM in liters. So make sure that your units are correct before you plug it into PivNert. Otherwise, the gas constant just doesn't work. This is your moles of the gas. From there, you can get 2 grams, or if they give you grams, you can get to moles and then plug it in. Lots of options there. You can also relate this to the density of a gas. Density. So density is typically given in grams per liter. Okay. We can go from moles to grams using the molar mass. So if I were to rearrange this equation for density, it would be equals P times the molar mass all over RT, because density has the mass and the liters, or the volume, built into it. So density equals PM over RT if they ask you to calculate density. Before we really dive into Dalton's law, let's talk about the normal units that we have for pressure. Pressure can be in standard atmospheres, which is the most common for chemistry, because 1 atm is the normal atmospheric pressure at sea level. The SI unit for pressure, though, is in kilopascals, so it's 101.3 kPa. Kilopascals is equal to 1 standard atmosphere. This is also equivalent to 760 torr. Now, torr is based off of old barometers, which used to have mercury in them, and so they would measure the millimeters of mercury that the atmospheric pressure would change. So we don't use mercury barometers anymore because they're kind of dangerous, but those are the 3 common units that we have. So that's how you would use to convert to ATM if you need it for the ideal gas law or for anything. Dalton's law has to do with mixtures of gases. So Dalton studied these gases and their gas pressure, and he figured out that if you have a mixture of different gases, each gas will affect the pressure proportionate to the number of moles of the gas in the container. So if I have a 50-50 mix of gas triangle and 50-50 gas of gas square, they would each contribute half of the pressure because each one has half of the moles. It doesn't matter that the triangle gas or the square gas are different sizes. It depends on the moles of the gas. Or if I had a different container, maybe I have 6 moles of triangle gas and 4 moles of the square one, then 60% comes from the triangle and 40% comes from the square in terms of pressure. So what does that mean mathematically? Now, so the total pressure is equal to the pressure of the individual gases, pressure A plus pressure B plus pressure C, etc. They just add up. Or in this case, the pressure of the triangle ones and the pressure of the square ones. But also, because it's based on the moles, you can grab a different kind of relationship there, where the the pressure of the one substance, pressure of A, is equal to the total pressure times the moles of A over the total moles. This is called a mole fraction, which is essentially kind of what I did here, but that's in percent instead of fraction form. What fraction of the gas molecules are the one type of gas, and that will be that same proportion of the total pressure will come from that one gas. So in this case, if we assume each one of these is a mole, right, I'm going to say I have 6 triangles out of the 10 total particles. And let's say that the total pressure in here is, 8 atm. So I would say the total pressure is 8 atm times the 6/10 would give me the pressure of just A. So the pressure from just from the triangles. Pressure of just the triangles in the substance would be 6/10 of 8, or 4.8. And that's how you would solve that Dalton's law problem. Okay, let's look at another application of Dalton's law. Sometimes we have to collect gas over water. So this is my container of water. And if I'm collecting a gas in this container, okay, this is water, some of the water molecules will evaporate. That's due to what's called the vapor pressure of water. So the vapor pressure is the pressure exerted by the gas that came from the liquid as it evaporated. Now let's say we also have our other gas in here. So the total pressure inside this container is equal to the pressure of the water plus the pressure of whatever the gas is that you're trying to study. So let's say we measure this volume here, and we measure that it is 193 milliliters of oxygen gas. And it was collected over water one day. The atmospheric pressure was 762 torr. The temperature of the water was 23 degrees Celsius. And vapor pressure at this temperature of water is 21.1 torr. Okay, so the vapor pressure changes at different temperatures. At higher temperatures, more of the water will evaporate, so you'll have a higher pressure. So that's why you have to take a look at the vapor pressure at any given temperature. So the question here is, what is the pressure of just the oxygen? Well, then I can use Dalton's law. The total pressure is the same as the pressure in the room, 762 torr. The water vapor pressure is 21.1 torr. And so then the other pressure is the pressure, it must be the pressure of the oxygen gas. So you can just subtract to find the pressure of O2. And you get it at 740.9 torr for the pressure of just the oxygen gas. Now from there, it might ask you something like how many moles of the oxygen gas were collected. So I'm going to go ahead and erase this since we used it. And we're going to use the ideal gas law to find the moles, PV equals nRT. Now that I have the pressure of the oxygen, I just need to convert it. So 740.9 torr, if you divide by 760, that will put that in ATM. The volume must be in liters, so 0.193 liters. Moles is what we're looking for. 0.0821 is our constant. And the temperature that we had was 23 degrees Celsius. So we need to put that in Kelvin, which is 296 Kelvin. Now that we have everything in the correct unit, we can solve for the number of moles. And you get that there was 0.00774 moles of O2 collected. So that's kind of how we would use Dalton's law and the ideal gas law to find different information about this particular experiment.